I'm Norman Wahlberger, and today we're going to introduce the simplest symmetries into hyperbolic geometry. These are the reflections. And there are two types of reflections, typically, reflections in points and reflections in lines. One of the remarkable features is that we'll see that they are the same here in hyperbolic geometry. So the symmetries of a geometry are closely connected to a branch of mathematics called group theory. This was made explicit by a prominent German mathematician, Felix Klein, in the late 19th century. In his speech to the University of Erlangen, he advocated a program or an approach to geometry where geometry is a group of transformations acting on a space. So to Klein, that was a way of encoding what geometry actually was. Different groups acting on different spaces give us different geometries. This is a very important historical, motivating idea, and we are, in some sense, going to follow it, but we're also going to transcend it a little bit. So one important little comment to make here for mathematicians and graduate students watching. Usually, Klein's Erlangen program is taken to mean a group of transformations acting transitively on a space. In other words, where we have a homogeneous situation where all the points in the space look the same. That's not good enough. We really need to enlarge our point of view to consider groups acting non-transitively. It's going to be very important for hyperbolic geometry. And I probably should also mention that the recent development of chromogeometry, which you can learn about in my Wild Trig series, or you can Google it and find a few papers of mine on it. This also shows that Klein's Erlangen program really has to be transcended, because in chromogeometry we have three groups of transformations acting on the plane. Okay, what are we talking about here when we're talking about symmetries? Well, let's just give a few examples to orient us. So if we're just working in the plane, then familiar symmetries are translations. So if we start with this figure here, say, then going from here to here, well, that's a translation. We're just shifting it, but we're not changing its orientation or rescaling it in any way. A rotation, we could rotate this thing to there, probably some point down here would be the center. We can reflect the image in a line. So the reflection of this in, say, that line there, a mirror image, would be this figure over here. There are also things called glide reflections, where we take our image and we reflect it and also move it. So if we reflect it in, say, an axis like this and translate it at the same time, then we could get this one over here. So going from here to here is a glide reflection. Here is a different kind of reflection. From here to here is a reflection in a point, which is also the same as a rotation in that point by a half turn, or 180 degrees, if you like degrees. This transformation here is changing the scale, but it's still maintaining a lot of the properties. That's a dilation. But there are other more sophisticated kinds of transformations too. For example, we could simply look at this thing from some strange angle and take a picture, and that would be also some kind of transformation, a perspectivity, or more generally a projection. And you might be able to get images that look like this if you take pictures of things, and especially if you allow yourself to take pictures of pictures. So group theory, symmetries are all concerned with these kinds of transformations. Let's start with the simplest ones, which are the reflections, and let's look first at what they look like in Euclidean situation. So let's start with the simplest Euclidean situation, which is the one-dimensional situation. We're just talking about points on a line. And since we're in the Euclidean situation, we'll talk about points with capital letters. to distinguish from the projective situation where universal hyperbolic geometry lives. So if we have a point A on a line, then we have the idea of the reflection in A, which sends this point B to this point C and sends this point C to this point B. And we're going to introduce this notation for that reflection. Greek letter sigma with a subscript A. That's the reflection in the point A. And our notation for writing this is this here. So we're going to say that B is C followed by the reflection A. In other words, C reflected by A gives B. Or conversely, B reflected by A gives C. So we're going to write the object first, the point there, and then the transformation to the right of it. That's our convention. Now if we have coordinates on this line, suppose that's the coordinate a, that has coordinates little b, that has coordinate little c, then we can see here that this is being the midpoint here is going to have the average coordinate. So a has to be b plus c over 2, the average of these two coordinates. And then if we solve that for, say, c, we get that c equals 2a minus b. So this little formula here is giving us what the reflection in A is doing to coordinates. If we reflect in A, then the point B is sent to the point C, which is 2A minus B. Now, one of the nice things that we can do with transformations in general is we can compose them. So we can do one, and then we can do another. And that's a kind of multiplication. It's not a multiplication of numbers, it's a multiplication of transformations. So let's have a look at that in this one-dimensional example. Suppose we have 2 points P and Q. And we first consider reflection in P. So let's say, starting with this arbitrary point X here, we reflect it in P, and then we reflect that point in Q. So the effect is, we're starting with X, and then we're reflecting in P, so that's X followed by sigma sub P, and then to that point we're reflecting it in Q, that's following it by sigma sub Q. And that's how we define the product of the two reflections. So sigma P times sigma Q is simply that composite transformation. In this case, it's a translation. If you start here, you end up here. You can check that if you started here, well, you would first reflect by P and then you would reflect by Q. You would still end up going from here to here, exactly the same translation as this one here. Turns out to always be translation by twice the vector P to Q. All right, so first exercise, check this geometrically and using coordinates. So still sticking with the Euclidean situation, now let's look at reflections in points and in lines. There are two types of reflections in planar Euclidean geometry. Let's consider reflection in a point first. We'll still call it sigma sub A, A being the point, right there. What does reflection in that point do? Well, it sends any point B to the other point on the other side of this line, which is an equal distance or an equal separation from A as is B, just on the other side. So B prime is B followed by sigma A. And similarly, if we started with that point there, reflecting it in A would give that point C prime up there. If we had a little figure, say something like this, and we reflected the entire figure, so that tip of the nose goes to the tip of the nose, the right foot goes to the right foot, and so on, then the figure is in fact rotated by a half turn. Now, one of the properties of this transformation is that it preserves orientation. What does that mean? Well, in the Euclidean plane we have a notion of clockwise and counterclockwise. So this thing here, this direction of rotation, it's counterclockwise. And if we follow that circle there and then follow its image under the reflection, we end up with a rotation which is in the same direction. So positive orientation there gets mapped to positive orientation there under this reflection. So we say that this reflection is orientation preserving. Now a little remark here about if you actually want to do this geometrically, the ancient Greeks of course knew how to do this, you need a compass. You can't just do this with a straight edge. So if you have a point A there and you want the image of B under this reflection, to find this point here, it's easy enough to draw that line, but to find that point where it is, you need to have a compass. You can put the tip there, and draw a circle, and where it intersects gives you the other point. There's another type of reflection, perhaps a more familiar reflection, because it's actually more commonly used. It's the reflection in a line. It's the idea of a mirror. So here's our line that we're going to reflect in. And how do we reflect in that line? Well, suppose we have a point P. We want to find its image. Well, the first thing that we do is we draw a line from P towards the mirror perpendicularly. That's a perpendicular altitude from P to the line L. And then once we have that altitude, wherever it meets, we're going to go an equal separation on the other side. In other words, we're actually going to reflect P in this point here. So that segment equals that segment, and that tells us how to go from P to P prime, the reflection in the line L. So we're going to use almost the same notation, sigma sub L, but this time L is a line. Now, here's the image of a little person under this reflection. And you may notice that it's a little bit different from this one here. This person has changed from being right-handed to left-handed, or vice versa. In general, if you have a little orientation like this, say in the positive direction, when you reflect it, you end up going in the opposite orientation. So this is a transformation that reverses orientation. So there's a big difference between reflection in a line and reflection in a point in two-dimensional Euclidean geometry. Now, before we go to the hyperbolic case, let me just mention briefly what happens if we go to 3 dimensions in the Euclidean setting. In 3 dimensions, there are really 3 kinds of reflections. We can reflect in a point. So if that's the point we're reflecting in, then the image of this point would be that one, while the image of this point would be down here. The image of this point would be here. Another kind of reflection that we can do is reflection in a plane. If that's a plane, then the image of this point would be that point. The image of this point would be that point, and so on. But there's a third type of reflection, the reflection in a line. So if we wanted to reflect this point in that line, we would go perpendicularly to the line and equal spacing out to the other side. So the image of this one would be this one. The image of this point would be this point. The image of this point would be that point. 3 types of reflections in 3-dimensional space. So it's important to gain some experience with these kinds of transformations, even just in the Euclidean setting. So here are 2 exercises for you to think about. So first one, if that P and Q are points in the Euclidean plane, then if we reflect in P and then we reflect in Q, then the effect is translation by 2 times the vector PQ. So for example, there's P, there's Q, there's some random point X. If we reflect X in first P, and then take that point and reflect it in Q. So that's X, followed by sigma P, that's that point there, then followed by sigma Q, that would be that point there. Then the effect of going from X to this, which we can also write this way, is simply translation by exactly twice the vector PQ. And this is sort of a corresponding result for composing reflections in lines. So suppose that L and M are lines in the Euclidean plane. Then show that sigma L times sigma M, in other words, what you get when you first perform reflection in L and then perform reflection in M, is either a rotation or a translation. Here's a situation where we have a rotation. This is the line L, this is the line M. They happen to meet. Here's some random point X. So first we reflect X in L, and then we reflect this in M. So to go from here to here is actually a rotation. In fact, it turns out to be a rotation about this point here. So the entire plane is rotated with center that point there, and the rotation is twice the angle between these two lines. Now the other case happens when the two lines don't meet, because in Euclidean geometry lines can meet or they can be parallel. If the lines are parallel, say L and M, we start with a point X there. If we reflect first in L and then in M, then the cumulative effect is to translate by, well, you can check twice the parallel separation between the two lines. So you can try to check these things geometrically, and even better, you can check using some calculations. Now let's move to the hyperbolic setting, which is what we're really interested in. In universal hyperbolic geometry, there are also two types of reflections. There is also a reflection in a point A and reflection in a line L. Now I remind you that in hyperbolic geometry, we're going to use little letters for points and capital letters for L, the opposite of what we do in Euclidean geometry. So our reflection in the point A will be sigma little a, and our reflection in the line L will be sigma of capital L. And then a very important result that we are going to establish is that if the line L happens to be the dual of the point A, then the reflection in A is the same as the reflection in L. The two types of reflections are the same, in fact. There's really only one kind of reflection in universal hyperbolic geometry. There's a big difference between this and Euclidean geometry. Another big difference is that the projective plane is not orientable. There is no notion of counterclockwise or clockwise rotations in our hyperbolic plane. Another big difference is that the symmetry group of the hyperbolic plane is very rich. Well, the Euclidean symmetry group is also rich, but in hyperbolic geometry the symmetry group is much richer. In fact, it turns out to be one of the most important groups in group theory. It's a very rich group which goes by various names. Sometimes it's called SL2, sometimes it's called the Mobius group, and sometimes it's SO21. It has various incarnations. So we're going to see the richness of this group. It's going to be a main theme as we progress in our understanding of hyperbolic geometry. However, I want to emphasize that the starting point, the basic generators of the group, these fundamental reflections, sigma A or sigma L, are in fact very simple and elegant. And they are very accessible to drawing figures by hand, which I'm going to encourage you to do. So, how do we define reflections in the hyperbolic setting? So I'm going to start informally here, or rather geometrically. I'm going to show you pictures and I'm going to define these reflections pictorially. Later on we're going to define them somewhat more officially, algebraically. But I want you to start with a very strong physical understanding of what these things are. This is a diagram I want you to understand completely. Okay, very important diagram. This is the definition of reflection in a point A, called sigma sub A. Okay, so there's our basic circle, our null circle. Here's a point A. I happen to be drawing it outside, but it turns out that it doesn't matter where this point A is, we can still define what we're just about to do. Okay, so right now, here's the point A. We are reflecting in this point A. And now we're going to choose a point that we want to reflect. Let's say this point B. We want to reflect this point B in this point A. So we want to define C, which is B, followed by reflection in A. What do we do? Well, first step is to draw a line through B, which meets the null circle in 2 points. Okay, in this case, B is inside here, so pictorially, pretty well anything that we do will work. If B was outside, well, we might have to choose that line carefully so that it actually met the circle. That's the first step, to choose that line L. So now you have 2 null points that this line L meets the circle at. Now we join those null points to our center A. Those 2 lines meet the circle in generally 2 other points. Those 2 points there. Now we have 4 points. This should be looking a little bit familiar. We sort of like 4 points, 4 null points especially. Okay, what do we do with these 2 new null points? Well, we join them with a new line. And what do we do with this new line? We see where it meets the line AB. Where it meets the line AB is the point C. So the reflection of B in A must lie on this line AB, and exactly there is where it is. That's the reflection in A of B. And if you reverse the process, if we started with C, well, we could use this line as our initial line. We would draw those 2 lines, find these new intersections, find that one there, and then we would get the point B. So this is a reversible process. The reflection of B in A gives C. The reflection of C in A gives B. So I hope you were saying to yourself, how do we know that that actually works? There's an issue here about whether this is well-defined definition. What's the issue? Well, our construction depended on this line L that we chose through the point B. So here's just a repeat of that construction. We chose L. Those are the 2 green lines. Those are the 2 new null points. There was the point C. The question is, what happens if we choose a different line through B? Let's say this dashed line there. Let's call it M. Well, then we would get 2 different null points. And when we join them up with A, we would get these 2 different dotted or dashed green lines, meeting the circle at 2 different null points. Then we have to connect those 2 null points and see where that line meets BA. And lo and behold, we get the same point C. So, this is well defined. C does not depend on the choice of line L or M through B. We could choose any line through B as long as it meets the circle and go through the process. We would always get that point to be the reflection. Now please check this. Draw some diagrams, get out your disk, draw some points A, use different points, different places, check that this is true. I want you to get some appreciation for the beauty of this result. Well, we haven't proven it yet, this claim. Another important and somewhat remarkable property of these reflections is that they send lines to lines. What does that mean? It means if we start off with a line, say this one here, let's call it M, and we look at various points that lie on it and compute the reflections of all of those points. The reflection of B is C, the reflection of B1 is C1, the reflection of B2 is C2, and so on. Then we find that all of these reflected points, C, C1, C2, also lie on a line. So every point on this line ends up being reflected to a point on this line. And that's true not just for this line, but true for any line. You choose any line, all the points on it, when you reflect it, they end up on some other line. So if the line is capital M, then this new line, the image of M under this reflection, we should also have an expression for that. And one thing that we could do is we could write sigma A of M with the M on the right-hand side now, sort of to alert us to the fact that we're acting now on lines rather than on points, minimizing perhaps our possibility for confusion. And another interesting remark is that, an important remark, that as it will turn out, is that this reflection also sends null points to null points. So if we look at the special case where the point that we're considering is that one there, say if we move this point up towards there until it's a null point, then the image moves up until we get that corresponding null point. And that's just the other null point that lies on the line joining B and A. That's in fact a very simple thing to calculate. So the image of B, just join it up with A, see where the other place where it meets the circle is. That's the image of B under the reflection in A. Similarly, the image of this one is this one under the reflection. So the reflection acts particularly simply on the null circle and sends every point on the null circle to another point on the null circle. It's going to be very important for us. Now I'd like you to get some experience in seeing how reflections work in practice. And so here is a bunch of examples showing what happens when we reflect in this particular point A. So this is reflection in this point A. And it'll be simpler if I also show you what the dual of this point A is. Here is its dual line A perp. Okay, so what happens to various points? The way I've marked this is, you see this point X here with this blue dot? Well, here's X prime. That means the image under sigma A of X. So the reflection in A sends this X to that X prime. Sends this little square to that little square. So if we choose a line through A, it's often simpler just to look at a line through A. Then this point is sent to that point. These points are actually interchanged. These two triangular points are interchanged. These square null points are interchanged. Then if we move outside, that point there is moved to that point there. And as we move outwards from the circle, this reflected point moves rapidly in that direction. And before too long, if we're moving along here, the reflected point goes to the line at infinity and comes out the other side of this line. So once we get to this point W there, its image under the reflection is actually W prime over there. So the image changes, or seems to change quite dramatically. As we're moving from here to here, the image of this point here is shooting out in that direction, and then at some point it actually gets to the line at infinity, because remember our projective plane has a line at infinity, and then after that it comes in here and then it moves towards A as the point moves towards A. Here's some other examples of that. Here's another line, this one not going through the null circle. Image of this one is this one, image of this one is this one, image of this one is, well, it's no longer in that direction, it comes out at the bottom. And as we keep going here, the image of this one is this one, and once we get to the dual line, the image is itself. And now you can see that the reflection in A is really acting a lot like what you might expect a reflection in a line to look like. This point goes to that one goes to that one, this one goes to that one. The line itself, the dual line, is maintained under the reflection. Everything is fixed. That's an example of reflection in a point A, and I want you to check some of those things, to draw lots of diagrams so you get a good sense of what reflection in a point looks like. That was a case where we had A external to the circle. It's also interesting to look at the other case when A is inside the circle. So here's a situation of reflection in the point A, which is right there now. So this point here is sent to that one there. This one goes to that one. This null point goes to that null point. this point y to that y prime there. This triangular point gets sent to there. And this point here gets sent to itself. Along this other line here, reflection in A, x goes to x prime, this point to this point, this one to this one, this one to this one down here, and then this one goes to that one there. And that one point is fixed. And again, if you plot lots of points, you'll see that this reflection deserves to also be considered to be the reflection in this null point. Points around here are being reflected to points on the other side. And we'll see that more when we talk about reflections in lines more officially next time. What we need now is an algebraic approach that complements this pictorial visual definition. We want to pin things down, as always, by being very concrete and have algebraic structures in place. So that's what we're going to do next time. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.